everybody, my name is Phil and I will be talking to you about Clojure today. But first this is my beautiful accessibility slide. This shows you that the text on my slides usually will not be smaller than what you can see here, and also I'm notoriously bad in color palettes. I tried to sprinkle some of my slides with color. If you can't see these colors very well, don't worry, they are really not essential. And then I have a disclaimer. This is not going to be an introduction into Clojure. I'm not going to teach you Clojure, well, a little bit, but I will focus on the possibilities that arise when we use a programming language like Clojure or similar technologies. So I'll start with a confession. I love programming. I've been doing it for a while. First my agenda. I split it into 3 parts. So the first part is we want to find some boundaries that we want to tackle. Then we will reach beyond these boundaries by the use of software. And in the third part, which is a practical demo, I want to reach even further by the means of software development. And my confession is I love programming. I've been doing it for a while. I wrote my first program at the age of 10. I don't recall what programming language it was. Must be either COBOL or Fortran. But it's really a long time ago, and I've seen a lot of languages since then. But I do remember on which machine I started to program. And it was an 8088 with 4.7 megahertz and 640 kilobytes of RAM. Does anyone remember this machine? Yeah? Some? And it was the high-end machine, because the lower-end machine had only 128 kilobytes of RAM. And honestly, I don't know how you can program with so limited resources. But 640 was plenty. But this isn't a hardware history lesson. And I said I used a lot of programming languages afterwards, and I still love programming. And I bet I'm not the only one here. So who loves programming? Yeah, most of you, great. That's what I expected. Because it's the greatest job in the world. But have you ever asked yourself why you love programming? I mean, you might score a decent salary with it, or you might have pet projects that you don't get any money from. And actually, it's I was told, one of the best advices for people who are in the position of hiring programmers: never hire a programmer that doesn't have a pet project. So there is this money topic again. I want to get away from money. So what else could it be that makes us love programming? And I thought about that, and I developed this theory. And it has to do with dopamine. We don't solve problems because it's our job. We solve problems because the right chemical are emitted in our brains when we solve the problem. We get a kick out of it. And if we solve the same problems over and over again, business problems are not that don't come in all shapes and sizes. They repeat over time. So you solve the same problem again and again, and you get bored. You don't have the same amount of dopamine in your brain when you solve a problem for the 3rd time. So you need more complicated problems. So in a way, programmers are junkies. We solve problems for the kick, and we need more difficult problems over time. And I think if a software engineer is experienced enough, and a customer comes with a problem, and he has seen the problem or he has seen the problem already, in there, he will find a problem that is worth solving. So a problem that is difficult enough to be tackled. And that's usually when the most experienced engineers go, this problem is not difficult enough. Let's build a framework. Okay. So in my search for reasons to love programming, I came across a quote from the renowned Alan Kay, who said, "Computer science inverts the normal. In normal science, you are given a world, and your job is to find the rules. In computer science, you give the computer the rules, and it creates the world." So clearly, as programmers, we get to create worlds. That must be the greatest job. And I think it's similar. Joe Armstrong earlier this year at GOTO Chicago said in his talk, computer science is not science. And that's, in a more concise way, what Alan Kay here says. So we get to create worlds as programmers. And I came up with this idea that programming might be the only creative discipline in which you are only limited by your mind. And then I thought about this, and I realized this bold statement is obviously not true, because there is literature. And within literature, there is a special interest group with a very long tradition that is only concerned with finding the truth, commonly known as philosophy. And philosophy and computer science, I studied both, have so much in common, I don't even know where to start. And this is also not the topic of this talk, so I won't even start. But in philosophy, from one of the most influential philosophers from the 21st century, we find this quote, "Die Grenzen meiner Sprache sind die Grenzen meiner Welt." Or in English, "The limits of my language are the limits of my world." Ludwig Wittgenstein, in his doctoral thesis, by the way, the only book he published during his lifetime. Everything else was published after he died. And this is an extraordinary book. As a software engineer, if there is one book in philosophy you should read, it's this one. And it's not even long. It has an astonishing structure. It's built up as a tree. You should look into that if you're interested in philosophy. So with Wittgenstein, or first a tiny German lesson for you today, boundary translates to the German word Grenze. And Grenze also translates to the English word limit, which is kind of unusual if you just look at the sheer numbers of words in the dictionary of both languages, in the official dictionaries. It should be the other way around, where for every English word you have at least 2 German words. But in this case, it's the other way around. And there is a difference between, like on a etymological level, there is a difference between boundary and limit, but I won't get into this because nowadays they are used interchangeably. So Wittgenstein is talking about limits, boundaries. And with Wittgenstein, we have to ask, do the languages we think in limit our thoughts? And if we now take a step back from philosophy to computer science, still with Wittgenstein, we can ask, do the programming languages we code in limit our problem solving? And obviously they do, because as programmers we create worlds. And who are the creators of programming languages? It's other programmers. So these programming languages are worlds that were created for us that give us a way of thinking about problem solving. Now, if you have programming languages with different paradigms, you have different ways of thinking about solving problems. So each programming language has its limit when it comes to problem solving. So if we step even one step further out of this shared narrative we have, I might ask, does giving a talk with slides limit the presentation? And with this, I conclude my first part in the search of boundaries. So we have found a first boundary that I want to reach beyond, and I would like to invite you to reach beyond that boundary with me by transforming yourself from an audience to participants of this talk. And you can do that conveniently with your mobile phones. So please join the presentation by scanning the code or typing in the URL. And then we see if it blows up or if I was able to deliver some engineering work. I have to ask, did anyone succeed? Damn it. It doesn't look like you did succeed. Am I on the wrong presentation? Let me check. No, I'm not. Oh no, I'm offline. That's a problem. How do I get online fast? What did I do wrong? It looks like I'm connected. Disconnect. Connect. I should have gone with a wired network. Something like this. I'm online. So, 40 of you succeeded. Let me just... So, we were here, right? Okay. 41. Nice, so you had enough time to join, great. So now I can ask the same questions again. Something like, do you love programming? Or I can ask a question like, how many programming languages do you know? And I can ask questions like, do you have a favorite programming language? And you can answer all these questions with your mobile devices. And I give you a minute to do so. And then I'll continue and we can see what we learned. So, 48 of you love programming. That mirrors the response I got earlier. And then we can see plenty of you know 4 or more languages. So I'm kind of preaching to the choir here. But that's great. And about a little bit more than half of you have a favorite programming language, which is always surprising to me when someone has, because there are so many and they all have advantages and disadvantages. How can you have a favorite? They are all great. The statistics are really not the point here. I just wanted to collect some data that I can use in the forthcoming presentation. So what else have we learned? We have learned that 74% are using an Android system and some use iOS. Why is this? Actually, this is a twist in my presentation. This graphic should be way worse. And then I would say But this is this is a bad graphic. We should improve that. And I proposed that I improve it. And now I have to make it worse to show the thing. But let me propose that I improve this graph. And then, but when I do so, you will see some Clojure code. So first I have to ask, have you seen Lisp before? Or you can raise your hand, or you can use your mobile devices to answer. No one? Ah, damn it. Okay, yeah. Then I assume that some of you don't have seen Lisp before, so I have a couple of slides that cover like the basics before we dive into the code. So Clojure is a Lisp that runs on the JVM. And ClojureScript is a Clojure that transpiles to JavaScript. So by now you can actually use it in the backend to write your backend, and you can also write your frontend in Clojure or ClojureScript. And here's a first line of Lisp. And the thing that might be alienating to you if you have never seen it before is you would expect when there is a function call that this first parenthesis starts after the function that is called and introduces the arguments to the function. But in Lisp, this is not the case. You have a list, and this list with here two elements, the function println and a string, is in a context of an executable Lisp program interpreted as a function call. And the first element in the list is the function that gets executed, and all the remaining elements are the arguments to the function. So a simple addition would look like this. You have the plus, and then you have the arguments to the function. And of course, you can nest lists to have the result of another function be the input to the next function. So here you have to read Lisp from the inside out. First the multiplication gets executed, then the plus gets executed. If you, like me at school, used one of those, I think it was Texas Instruments calculators, you are used to the reverse Polish notation. HP? What? HP. Thank you. And then there are lists that don't get interpreted as a call, a function call. In this case, this is just a literal list. In Clojure, we call them a vector, but the square brackets say this is a literal list, and there are some implementation details concerning performance, why this is a vector. And in this vector here, we have keywords. And keywords are basically strings that only exist once in the memory, so they have only one memory allocation and are very cheap to compare. You find them all over Clojure code. And these data structures can be used to express, for example, markup. So here we have an example with HTML. We have a div. Inside of the div is a pre-tag, which comes with an attribute style, which has some styles, and then the content of the pre-tag. And this is just templating. It's just one way of doing templating. And you can use that in the back end to have the template for your for the website you want to serve. But you can also use that in the front end. And in the context of a reactive front-end framework like React, this essentially replaces JSX. So I have one example for you. We had this one student I'm teaching, and my business partner is also teaching at the same University of Applied Science. And we had this one student that approached us and said, okay, you showed me Clojure during my studies, and now I fell in love with Clojure, and I want to make my bachelor thesis, and I know what the answer is. The answer is Clojure. Can you help me and find the question? So we sat down and said, okay, so what's the unique selling proposition for Clojure? It's good in concurrency, but we are not good in concurrency, so don't do a concurrency topic. Let's do something more practical. It's a University of Applied Science. So we had this use case for a lecture capture tool, because at every university you have a lecture capture tool, usually with camera and streaming encoder and stuff, but you need someone to set it up. I can't set these things up. So usually they are off and they are not used. But the students would really like to have, besides the slides that we can give them, they would like to have a recording, because there is a lot of communication between the lines during lectures. So we asked, okay, how would an application look like where we can do lecture capture grassroots style? At the beginning, we will only do audio to make it simpler. We won't record video, also that's totally possible. And we said, okay, we need an API backend, that's the box on top. We need a web front end, which the students can use to listen to the recordings. And we need a mobile application for both platforms to use the recordings. And we ask, how is it possible to share code among all these platforms? And the answer is Clojure. Because in Clojure, you can actually share code for all these platforms. In that case, we just, validations is a good example. Validations is something you want to do in the front end for usability and also in the back end for security. And you want to keep these validations in sync. And it's really nice if you can share them in via a shared library between these code bases. So that worked out nicely. I continue with some more Lisp before I come to the practical part. So we can also, besides templating, we can use these data structures to write Lisp code. So here, this is a function definition. We introduce it with it's called a special form defin to define a function. Then I give it a name, I give it a list of arguments. This is the signature. And then in the body, I can have local variables, I can do computations, and I have an implicit return, and I can call the function in the last line. So Clojure code is written in its own literal data structures. And that, combined with macro facilities, gives you tremendous power over the language. Everything you know from other languages that falls into the category metaprogramming is replaced with these concepts. There is one last thing before we go into the code. Like many other functional programming languages, Clojure has immutable data structures, which is fine if you have an application that takes some input, transforms it, and gives an output. But as soon as you have a running system that has to keep track of a state, you are out of luck with an immutable data structure because the data can't change. And there in Clojure, you have atomic references. So with this function atom, you can create an atomic reference. You give it an initial value, here an empty map. And then you can dereference that atom to access its value. And you have a clear interface to change it. And when you change it with special functions, if you try it in any other way, you will get an error. If you change the state of the atom, you do it implicitly within a transaction. And Clojure has this built-in implementation of software transactional memory. And that way you can, it's really good for concurrent problems because it's built in on the language level. You don't need to take care of that yourself. And you can only write the atom if nothing else in the meantime has written it after you read it and stuff like this. And in combination with the reactive frameworks like React in the front end, this is extremely powerful because in Clojure it's possible to hook up the changes of state automatically with the function called components that transform the state into the visual representation. If you're interested in this theory, how it works, there is this great article, very short read, just 2 pages, that gives you an impression on how Clojure works with state, and it's really helpful if you're coming from an object-oriented background to understand why it's behaving so differently than you're used to. Okay, so now I want to go back to my presentation and, well, improve the slide, which already looked nice for some reason. So I go into the code here, and now I'm in the situation that I'm in my development system, and I would like to work with the data you provided by joining the presentation. So how do I breach that boundary? And since the data is stored in an atom, I can easily access the content of that atom and pull it into my development system, and I have a very opaque little utility for that I call plunder, which just makes the correct request. And now I have the data here on localhost in my development system, and I can start and hack away on that slide. I told you previously I wanted to improve it. Now I have to make it worse. It should look like this in the beginning. So now I can do stuff like this. Height and width is always something I mix up when I do visuals. What did I do? And then I can say, okay, but it's not really clear which one is which, so maybe we should rotate the text. And then we should give it some space, like this one and this one. And the thing I want to point your attention to is not that I have here hot code reloading. The thing is that I keep the state. Because usually when you see demonstrations in hot code reloading, you might even have a browser reload. It refreshes the page because something changed. And that's nice. I don't have to switch windows. That gives me some speed ups. But in more complicated applications, I usually have a whole ceremony to get to the step where I'm actually trying to fix something. So I carefully create the state in multiple steps. And then I'm somewhere where I have one shot to get it right. I change the code, one shot, and it's not the thing I wanted. So back, creating the state, and then I change it, another shot of getting it right. And here, I keep the state. I just change the logic of the code that transforms the state into the visual representation. And I don't change the state. This, by the way, also works if you are working with React Native on mobile phones. You can have your mobile phone that has the application running, and you change the code, and it hot swaps the code and keeps the state on the phone. It's really nice. I have one other example which makes this even clearer because it's more obviously a running system, and maybe I can find it here. So a year ago, I worked for this non-profit organization that cares about the orangutans on Borneo. And for a fundraising campaign, they wanted to have a little jump and run game on their website. And I made a really fun jump and run game with challenges. And then they told me, but in real life, the oil palms have always the same distance, which doesn't make the game really fun. But I don't want you to watch me the gameplay. I can make my point without the game playing, because it's still playing. You see raining clouds are coming into, there is a hornbill, majestic bird. And if you want to see the hornbill again, I can make changes here. Like I can do crazy stuff, like this one, which switches all the sprites and makes it a little bit surreal, so maybe change that back. But I can also search for my hornbill probability factor, and I can say, oh, I want to have way more hornbills coming in. And I just save the thing, the state keeps running, and then there is our invasion of hornbills. Okay, way too much hornbills. I don't want to get them cannibalistic. So less hornbills. Okay, back to my slides. Demo time. One last word about Lisps. If you get into Lisp, you will soon see this REPL thing. It stands for read, eval, print loop. And you have to read Lisp from the inside out. So first it reads some input, then it evals the input, which is hopefully code. Then it prints the result of the eval, and then it loops, which means it starts all over again. And what do you have? It's a command line. It's a command line into your programming language. And you can run that standalone to test out some code, but it's even more popular to have it inside of a running system. And if you combine it with a network, you can actually have your application open a port, and then you can connect to that REPL, and you can do the same thing that I showed you in the front end, also in the back end. You can hot swap code in your running system, and you can even do it on live production machines. I'm not saying that's always a good thing, but you can. Okay. I'm sorry, just for technical reasons, I won't be able to provide slides for this presentation, but I will open source the thing as soon as I ironed out the really ugly parts. So if you're interested in that, you can check our company's blog. And just in case you missed it, my 3 takeaways for you today were: learn as many programming languages and paradigms as you can, give Clojure a chance, and save the orangutan. Thank you.